cover chapter 10, 12 to 15. We pick one question from each problem set of each chapter, then we will elaborate more on how to solve them. So we picked 5 questions. First, chapter 10, question 16, chapter 12, question 8, chapter 13, question 12, chapter 14, question 5, and chapter 15, question 9. And we will go through each one of them. So let's start our first question, chapter 10, question 16. This is about 1/2 factor. So the problem is when this many of hydrogen chloride was dissolved in this many of water, the freezing point was minus 4.65 Celsius. The first question is how to calculate the 1/2 factor for the hydrogen chloride. Before that, we know how to calculate that. The 1/2 factor can be calculated from the freezing depression equation. So we need to know each one of them. The first one is the delta T is freezing point depression, is how much the temperature changes, the freezing point changes. Then I is for 1/2 factor, then constant Kf, and the morality of dissolved particle. So let's calculate it. First, we get the mole of hydrogen chloride by mass of hydrogen chloride divided by the molar mass. Then we get the molarity of, sorry, let me get a laser point. Then we get the molarity of hydrogen chloride by divided by the mass of the solution. So we get the molarity 1.32 mole per liter. We need to mole per kg is equal to 1 liter. Then we get the delta T is 0 Celsius minus 4.65 Celsius. Then we get the delta T. Then we bring all the number we just calculated into the equation. We can get our 1/2 factor. It's all based on this equation, so it's simple enough. Then the second question is, what is the percentage of ion pair in the solution? So before that, you need to know electrolytes do not always fully dissociate. There will be ion pair. Let's look at the diagram. When we put hydrogen fluoride into the solution, particularly in water here, it will be 3 particles. For example, like hydrogen ion and fluoride ion and hydrogen fluoride ion pair. So the ion pair also adopts particle in this situation. Then we need to know how the 1/2 factor is calculated. It is mole of the particle in solution divided by the moles of the solute dissolved, the total solute. So we can assume that we only have 1 mole of hydrogen chloride. So X mole of them exist as an ion pair. So we can know that how many are dissociated is 1 minus X. Then from the equation, we know the mole of hydrogen chloride equals to mole of hydrogen and ion are 1 minus X mole. So the total dissolved particles are the 3 of them combined: hydrogen ion, fluoride ion, and the hydrogen fluoride ion pair. So is this equation. And from part A, we calculate that the factor for the question is 1.9. So bringing into the equation here, the mole of the particles in solution, it's a solution we just calculated. The total dissociate is we have 1 mole of hydrogen chloride. So bring the equation, Van-Hoff factor is 1.9. So we can calculate the x is equal to 0.1. Then percentage, we can just directly calculate it. 0.1 divided by the 1. 1 more we have, then is 10%. Here you can write 10.1 or you won't lose point because of the rounding issue. Okay, that's the first question. Let's start our second question. It's chapter 12, question 8. It is how to use the ICE table. How to use the ICE table. So consider the equation. Hydrogen fluoride will be break down to hydrogen and fluorine. In this experiment set up 1 mole of hydrogen fluoride, 0.276 mole of oxygen, and 0.750 mole of fluorine are mixed into the 5-liter flask. First, we need to determine the reaction quotient, Q. In order to calculate that, we need to know how to calculate that. The reaction quotient is similar to the equilibrium constant, but it only uses the concentration at current moment to calculate the value rather than the equilibrium concentration. So current value, we can know that we have this many of hydrogen fluoride, this many of hydrogen, this many of fluorine. So we can calculate the concentration of them. Concentration of hydrogen fluoride is the mole divided by the volume. So they are all basically the same. Then we know all the concentrations, so we can bring to the equation. We can know the equation. The product side is on the top, and then the reactant side is on the bottom. So we know the concentration of hydrogen multiplied by concentration of the fluorine, then divided by the square of concentration of the hydrogen fluoride. Then we can get our reaction quotient. Okay, the second question is, will the reaction proceed towards the product side or the reactant side? Which way it will go? So before that, always we need to know some basic knowledge of that, how to determine the reaction will go each way. We will know it by the reaction quotient Q. If the reaction quotient Q is less than the equilibrium constant K, which is given, the net production will go to the product side. If the Q is larger than K, the reaction will go to the reactant side. If the Q is equal to K, the equilibrium is reached. So from the first question, we know our Q is 0.207. So we easily know that our Q is larger than the K, which is given. So the reaction will go towards the reactant side. It is larger. It will go to the reactant side. It will produce the hydrogen fluoride. Then the third question is, what is the number of mole of hydrogen fluoride in the flask when the setup reaches equilibrium? So this requires us to know how to use the ICE table, which is write it down here. Let us practice. First, we need to write the balance equation, which is given by here. Then write the equilibrium expression, which is the constant K is hydrogen fluoride with hydrogen fluoride. List the initial concentration list here, which is calculated by the first question. We know the hydrogen fluoride is 0.2, hydrogen is 0.05, fluorine is 0.15. Then calculate Q, which is know by now. Then calculate Q is we know Q, and the reaction will go to the reactant side. So we will gain the hydrogen fluoride right here and lose our hydrogen and fluorine. So the equation goes of hydrogen x of fluorine to produce 2x. There is a 2 right there. Produce 2x of hydrogen fluoride. This is our change. Find the change, then define the equilibrium concentration. So the equilibrium concentration after the change, we plus 2x minus 1x minus 1x. This is the concentration when it reaches the equilibrium. Then substitute the equation equilibrium concentration. So we know the equation, then substitute it by the equilibrium concentration we calculated in this equation. We can solve the x equals to 0.0468. This is rejected because when you move back, it will give a negative hydrogen concentration. So we use this number. Then we calculate concentration at equilibrium is 0.2 at 2x equals to 0.294. Then the moles of, which is the question, the moles of hydrogen fluoride is this multiplied by the volume is 1.47 mole. Okay. Okay, the third question is chapter 13, question 12, which require us to calculate the pH and the equilibrium concentration of all species presented in the H2SiO solution at 25 degrees. So from the 25 degree, we can know that the pH at the pOH equals to 13. Yeah, it will be bring up later. So in this question, some will just add to water, just dissociate the H2CO3 into the CO3, which is not correct because when you look at the K1 is much larger than the K2. So we can know that losing the first hydrogen is very easy, but losing the second is fairly difficult. So we need to divide it into 2 parts and then consider it. So we can use this equation. So we need to consider the first dissociation is H2O3 at 1 water equals to H2 CO3 at 1 water, HCO3 at 1 hydrogen protonate water. And the K of which is constant. So because K1 is much larger than the K2, we can assume all the protonated water is solution only contributed by the first dissociation, which is this. We don't need to consider the second dissociation will contribute to the CO3. So just change is X. So using the ICE table, we can know that based on this equation, we have three which is changing. The initial of which is 0.01. These two didn't exist before the equation. Then the change, we will lose one H2CO3 to produce one HCO3 and the protonated water. So the change will be lose one and add one, add one. So the equilibrium, we can calculate it like this. And Ka, which is listed by this, we can bring all the calculation into the equation. So it's and the base assumption will assume that X basically brings no effect to the concentration of the H2CO3. So we can simplify the minus X into just 0.01. So we can calculate the X equals to the protonated water, and the HCO3 equals to 6.6 plus 10 to 10 squared by minus 5. Then we calculated percent dissociation, which is X divided by the concentration of the H2CO3, which is 0.66%, which is fulfills the 5% rule. So our weak dissociation assumption checks out. So we really don't need to consider the X brings the effect to the concentration. So let's continue. There is the second dissociation. The HCO3 will lose one proton and become the CO3. And this is a K2 equation. K2 equation. So also use the ICE table. We list the initial concentration. But need to highlight this one. There are some, when dealing with the second dissociation, the concentration of protonated water is no longer 0. It will be produced by the first dissociation, which is X. So we list the initial concentration as 6.6 plus 10 to 15. And the change will be assumed by lose one of this, produce one of this and one of this. The equilibrium concentration is this. So with a weak dissociation assumption, we still can bring all the number into this equation. So we can get this equation right there. And the weak assumption simplify this by this, so the X is 5. Then of course we need to check 6 divided by 6.6. This is much smaller than the 5%, fulfills the 5% rule. So the assumption checks out. Then the concentration of the CO3 is 5.6. So we can conclude all the concentration we just calculated. Water and the HCO3 is 6.6. The concentration of CO3 is 5.6. H2CO3, which is we can neglect the X, which is also then we have how to calculate that. We need to calculate the pH first. The pH of the solution basically contributed by the protonated water, which is the proton. So we use this concentration to calculate the pH. Then we know the Kw, which is concentration of proton multiply the hydroxide. Hydroxide, sorry. Hydroxide ion is 14. Yeah. So we can calculate the concentration of the hydroxide ion, which is this divided by the concentration of protonated water, which is this. It's a lot to take in, but just remember we need to look at it at first part. The first dissociation will lose one hydrogen atom, and then the second dissociation will lose the second. You cannot use this equation, just get the final result. Okay, the fourth problem is chapter 14, question 5, which is calculating the pH value. This is a question basically about titration. So consider the titration of 40 ml of hydrogen fluoride with sodium hydroxide. So how many milliliters of base are required to reach the equivalence point? We need to know the equivalence point. Most of the base we added equals to the acid in the solution. So it's more, so we can get the equation concentration multiplied by the volume equals to the concentration of acid equal multiplies by the volume. So we know the concentration of sodium hydroxide, and we know the concentration of hydrogen fluoride. We all bring them into the equation so we can get the volume of sodium hydroxide, which is 50 ml. Okay, we need to calculate the pH at each following points. First, at the start of the titration, when we begin the titration, how much is the pH volume? So at the start, there is a weak acid of hydrogen fluoride, so we can determine it by the ICE table using this equation. There was no base, so only the hydrogen fluoride add water to protonated water and the fluoride ion. So we list the three concentrations. The initial concentration we know is this, and both of them are not exist just yet. Then we lose one of the hydrogen fluoride to produce one of each. So the equilibrium concentration is 0.5 minus 1. And the equilibrium concentration for this two is just x of the chain. So of course, with weak assumption, we can simplify this to this equation. Ka is the last two divided by the concentration of the hydrogen fluoride. Now we can get the concentration of protonated water, which is x equals to this, but is not important. So just know the proton concentration, so we can calculate the pH by this pH 0.0. this is the start. If you decided to don't use a weak dissociation assumption, it's basically the same, just bring in all the equations. So it's 2.04. It's just a option, but you can use both. You can write both, and it's all correct. Okay, let's calculate the pH of the after addition of 10 ml of the base. So we need to know this equation first. So if the base is added, then we can use this equation, base plus acid into the fluoride ion and water. It will use water. So we need to know how much the acid is neutralized by the base. So we need to calculate the concentration of the base we use. Is this multiplied by the volume is the concentration we used. Mole we used. This will do the how much mole of acid. So we can calculate the concentration, how much acid left. So how much acid in the original solution is this multiplied by this, then we can minus this because it's neutralized by the base. Then we divide it by the total volume, which is 40 ml, then add 10 ml. Then we need to calculate the fluoride ion concentration, which is the how many are already neutralized. So this is the mole of the neutralized, then divided by the total volume. So we can calculate concentration. Then we will bring this back to the equation. So pK at the log 10 fluoride ion divided by the hydrogen fluoride ion, hydrogen fluoride. So we need we know the pK, which is this. Then fluoride ion concentration, hydrogen fluoride. Then we can calculate the pH of the solution. Now, the third one is halfway equivalence point, which is a lot like this, but is more straightforward because you are halfway to the equilibrium. So just like this equation, so the concentration of fluoride ion is equal to the concentration of the hydrogen fluoride. So just bring that back to the equation, pK at this divided. So it is basically the same. So it is written by 1, and we can calculate the pH. So at equivalence point, we just calculated we need 50 ml of sodium hydroxide to reach the equivalence point. So from the first part, we know the volume. Then at the equivalence point, all the hydrogen fluorides are neutralized by the sodium hydroxide. So they're basically salts. So we can calculate the concentration of fluorine, which is how much is the moles of this hydrogen fluoride is divided by the total volume. We cannot use this mole per liter directly. We must consider the volume range. So we calculate the moles first, then divide it by the total volume. Then we can get concentration. Then we need to know the equation Ka multiplied by Kb equals to Kw. Here we are at Kw is minus 14. Ka we know. We can directly bring into the equation. So we can get the Kb. Then use ICE table to write down fluorine is which is this equation. Just hydrogen fluoride equal plus water will produce fluoride plus water equals to hydrogen fluoride equals to hydroxide ion. So based on this equation, we can know that the fluoride ion, the concentration we just calculated, there was no hydrogen fluoride left. So we use, this is -1 plus 1 plus 1. So we can get the equation for Kb is hydrogen fluoride multiplied by hydroxide ion divided by the fluoride ion. With weak dissociation assumption, we can simplify this into the 0.111. So we can get the X, which is equal to the concentration of hydroxide ion. Then we know the concentration of hydroxide ion, we can calculate the pOH, which is this equation 5.75. Then we can use 14 to minus pOH. We can calculate pH, which is 8.25. Okay, the last two question is how much is the pH at when you add 80 ml of sodium hydroxide, and how much is the pH when you add 100 ml of sodium hydroxide? The first one is fairly easy. When you add all the sodium hydroxide, you can neutralize all the hydrogen fluoride, and then the hydroxide ion will be exceeded, will be the only thing to determine the pH. So we just need to calculate the hydrogen, how much the hydrogen, how much is the sodium hydroxide is left. So this is basically how much the sodium hydroxide we added and how much is used by this acid is neutralized. So we minus this concentration, we minus this mole, then we divide it by the total volume. So we get the concentration of hydroxide ion. Then we can calculate the pOH by this hydroxide ion. Then we can get the pH by 14 minus pOH. The last question is basically the same, just substitute 80 ml into the 100 ml. It's basically the same. So the third question is sketch the titration curve and label the equivalence point. It is fairly easy because we calculate all the points, how much the sodium hydroxide added is 0, 10, 25, 50, 80, 100. Then all the pH. So we can get our graph. This is slowly rising. pH is slowly rising. Then we label the equivalence point, which is the pH equals to 8.25, and we add 50 ml. And then based on this graph is given, suggest the indicator is suitable for this titration. how to decide the indicator? So we need to decide it by the equivalence point. When we reach the equivalence point, it is 8.05, 8.25. So just run here, run here. We know that field of the indicator is around that point, but we need to know the indicator must change its color around that point. So this is out. This is out because it's basically red, and this is out, basically red, basically yellow. So this three is okay. So we should pick this three as our indicator. Yeah. So the last question is chapter 15, question 9. To decide the concentration of iron, silver iron, 然后 and then AgNH3 ion, AgNH3 ion in the solution prepared by the silver nitride to the ammonia, we can know the KF value, assume no change in the volume. So before this question, we need to know how to know the initial state of the reaction. We look at the Kf value. The Kf value is fairly large. The Kf1 is 2.5 by the positive of the 10. So we will decide it will lie very close to the product side. So we can't use the we cannot use this equation directly. Oh, sorry. We cannot use each equation that for silver ion at 1 of the ammonia, and then at 1. This is not correct. It will cause a lot of problems because when you calculate the concentration of iron, silver ion, and concentration of this, it will still go to the reaction to the end. It will become this ion. So we need to decide how the reaction will proceed. So if the Kf value is fairly large, we just assume all the silver ion will convert it to the silver ammonium 2 ion. So this is the equation. And from this, we can assume the concentration of the AgNH3 initial concentration. Initial concentration will be all of the ion react to the product side. So the concentration is this, and the concentration of the ammonia is this. So we need to backward think this. First, we just assume all the reactant are going to the product side. Then we need to consider the dissociation. So the first dissociation will lose 1 ammonia to this ion. We know the initial ion, the change will lose 1 of this to produce 1 of this and 1 of this. So we bring this all into the K value. Note that this is opposite of the Kf2 because we are considering the dissociation, not the reaction itself. So it was backwards of the Kf2, and we'll bring into this and calculate the X volume, the calculated X, which is equal to the concentration of silver ammonia. So we consider the second dissociation by losing another ammonia. So we using the ICE table and calculated by the KF1 because the concentration of iron and ammonia is divided by the iron ammonia ion. Then consider the weak dissociation. It will simplify to this. Then we can calculate the X equals to, which is equals to the concentration of iron. So because the weak dissociation, the iron basically unchanged. So the concentration of ammonia 2 is 0.1. The concentration of ammonia 1 is 4.4. The concentration of silver ion is this. Yeah. This is basically all the question we had. Thank you for listening. Thank you.
Okay, so thank you. Thanks our TA for like spending like 45 minutes to like share with us all the questions.
Yeah,
so
it's
any
a bit
questions?
Sorry.
Yeah. Sorry.
Sorry, it's a bit lot than I
It's okay.
imagine.
It's okay. Yeah, it's okay.
Sorry.
Like so, we actually have an in-depth elaboration. That is good. So if you have any questions, okay, feel free to ask us. You can either like use the mic or actually like type on the chat box. Okay, and if you have no other questions, feel free to leave. And good luck in your exam. If you have questions, feel free to type on the chat box. Will the material shared in Canvas again? Hey, Ken, is that uploaded yet? Is Ken here? I can't hear you. Although you unmuted yourself, but I cannot hear you. Hi. Oh yeah. So Ken, will the content be shared or already shared yet? The slides. I don't remember actually. Okay, so the slides will be uploaded with the video. So basically, we might take like a few hours to half a day. Then you will have all the things like uploaded on Canvas. Okay, and another question is like our TA, please turn to chapter 15, question 8. Chapter 15, question 8.
15, question 8.
So that is the last one, is it? Oh, that is question
no.
9. Oh, I
Yeah,
see.
it's
So
not in our PPT.
I see. Ken, do you have like the question around? Do we need to calculate the percentage dissociation to show that yeah, if you want to double check, please double check the 5% rule if like that is being asked in the like long question. Okay, if it is in the long question in 30%, you should show your steps. So if you use the 5% rule, just write down, okay, you use 5%. Okay, chapter 15, qualitative analysis. Okay, I can just speak here. Okay, so for the first one, if you want to separate the silver and copper, you can just add sodium chloride or hydrochloric acid, anything with a chloride ion. Basically, because silver chloride will precipitate while copper chloride, most of the chlorides do not precipitate. So if you add HCl or sodium chloride, then you will actually precipitate out silver chloride, and that's why you can filter out the silver salt and then leave the copper salt behind. And the second one is like potassium and magnesium. Potassium, magnesium, you can add carbonate or sulfate. Basically, carbonate or sulfate will form insoluble salt with group 2, like ions. And that's why magnesium sulfate or magnesium carbonate, then they will stay behind. And then potassium sulfate will not. And that's why if you add sodium sulfate or sulfuric acid, then very likely you will precipitate out the magnesium salt, and then you can filter it out and then leave the potassium ion behind. Okay, and the third one is like chromium, lead, and tin. Okay, chromium, lead, and tin. Hopefully you still remember, like lead is one of the case that if you use like the ions, if you use the chloride ions, okay, it will precipitate out the the lead, okay, the lead salt, okay, because like there are several salts that are not soluble in the solution. Okay, so hopefully you still remember that. And then for the remaining part, you can use the sulfide. Okay, I think you can refer to our slides, and then in the solubility and complex ion slides, I think you can check that you have the steps. Okay, you actually have the steps, and you will see that the chromium. Okay, chromium will form is a base insoluble sulfide or hydroxide, while tin. Okay, tin actually is an acid insoluble sulfide. Yeah, so that is tin. So if you add H2S, or basically hydrogen sulfide, you precipitate out the tin ion first. So the tin 4+, you are actually going to precipitate out the acid insoluble sulfide. For the remaining chromium, it will still be insoluble. It will still be soluble, so you will leave that in the solution. But if you want to precipitate out, you can also add base to the solution, so that you can increase the sulfide concentration, and that's why you can actually precipitate out the chromium ions. Okay. Can I use? Sorry. Next one. Can I use sodium hydroxide for 8B magnesium hydroxide? Is insoluble. Okay, magnesium hydroxide, if you consider that to be insoluble, that's okay. But magnesium hydroxide is not that insoluble. So, well, I think there are better options. But if you really write down magnesium hydroxide, that is still kind of okay. Okay, hopefully that's okay for you. Any other questions? Chapter 10, question 10. Hey, Ken, please. Chapter 10, question 10. Oh, okay, this one. Okay, no problem. So chapter 10, question 10, that is about the mixture, the deviation from the Raoult's law, and which one is negative, which one is positive, which one is more likely to be most negative, which one is likely to be most positive. Okay, most negative one, most negative deviation means the two components have a very, very strong interaction with each other. They really like to mix with each other. Okay. At the same time, they should be somehow different. So in that sense, actually the most negative deviation should be 3, acetone and water. Because acetone and water, first, both of them are polar, and at the same time, acetone do not have a hydrogen bond. But when mixed with water, actually the acetone and water can form hydrogen bond. So there is a further stabilization by mixing acetone and water. And that's why that one is like the most negative deviation from the Raoult's law. And for the most positive deviation, basically you should choose the pair that is most incompatible. So the one is most incompatible is hexane and ethanol because one is non-polar and the other is polar. Okay, let's examine all the three cases. The first one is methanol and butanol. Like both of them are alcohol. They're kind of similar, although they have a different like length in the carbon chain, but they are still kind of similar. So if they have like they are kind of polar, they're kind of like forming hydrogen bonds. So it's kind of similar. So we will expect not so much deviation from the Raoult's law. Okay, hexane ethanol. Hexane ethanol is very incompatible. One is non-polar, one is polar. So you can see why. Acetone water is very compatible. You will see that actually when you mix acetone and water, the delta H is very negative because they actually have polar interaction. At the same time, you have extra hydrogen bond. The fourth one is tetrachloromethane and octane. Although tetrachloromethane looks like locally, they look like polar, but because the whole molecule is symmetric, so that is also non-polar. And octane is also non-polar. So that is more like non-polar. When they are mixed together, they do not have a very significant positive deviation from the Raoult's law. So the most incompatible one, or the one that is most unlikely to mix is hexane and ethanol, and that's why that one will give you the most positive deviation from the Raoult's law. Okay, hopefully that answers your question. Any other questions? Okay, Ken, can you please scroll up to question 3-4? 3 and 4. Oh, 3 and 4. Well, 3 and 4 basically you need to calculate the molarity. Wait, yeah, chapter 10, 3 and 4 is basically calculating the molarity and molarity. Okay, molarity. So the first one, like you said, you are basically having a density of 25% mass percent solution of the sulfuric acid. When you have the 25% mass percent, basically you have the weight percent or weight to weight ratio. And at the same time, you actually have the molar mass, the density, okay, the density. So based on the density, you can calculate, for example, if I have 1 liter, or you assume 1 liter or 100 gram or whatever, then you can already get like the ratio between the basically what is the mass, what is a concrete mass of a sulfuric acid and what is the mass of water. And based on the fact that, okay, water has a volume, okay, has a volume, you can get the like basically a volume, and also you get the mass, okay, mass of the sulfuric acid. You basically have a certain mass of the sulfuric acid. You can calculate the number of moles of sulfuric acid, okay, number of moles of sulfuric acid. So, okay, let's see whether I can annotate. Oh, good. Okay, so you basically have like the mass percent is basically 25% is basically if you, as a shorthand, I just write S for sulfuric acid and then water for W for water. Okay, so the mass percent is basically the mass of sulfuric acid plus mass of water as a denominator, and then the mass of sulfuric acid as a numerator. So if you can actually specify, for example, like 1,000 gram, okay, 1,000 gram is 1 kilogram. So if you specify 1,000 gram of the solution, then you can already get, okay, you can already get the mass, okay, you can already get the mass of 1,000 gram, And by the ratio, you know that 250 gram comes from the sulfuric acid. And if you get 250 gram, then of course you can calculate the number of moles of sulfuric acid. And at the same time, you know that, okay, when you have that number of moles of sulfuric acid, you also know you have 750 gram of water. And 750 gram of water, then you get the information of number of moles of sulfuric acid and mass of water, you get molarity. Okay, or in other words, if you want molarity, well, 1,000 gram, okay, 1,000 gram, you can actually use the density to convert that to the number of moles. When you convert that to the number of convert that to a volume, 1,000 gram will correspond to a certain amount of volume. Then that amount of volume, you use that as a denominator, you can calculate the molarity of the solution. Okay, that is chapter 10, question 3. Chapter 10, question 4 is, well, it's a similar idea. Basically, you need to, okay, the trick here is that you first like specify a certain volume or a certain mass. Then you can actually calculate, because all these are basically about composition. They do not depend on mass. So the idea is either you specify 1,000 milliliter or 1,000 gram, and then you make all the other calculations, then you will get a mole fraction. So I think the trick here, like I think you don't get the point, is for for question 3 and 4, you need to assume a certain mass and a certain volume. Then the later calculation will be kind of easy. Okay, yeah, hopefully that explains the issue. Ken, chapter 13, please. 13, question 13. Or maybe, yeah, 13 first. 13 and then 3, okay? Oh, 13. Oh, I see, okay. Chapter 13, the question 13E. 13E is, oh, I see, okay, 13E. How do we get the 13E? 13E, you need to compare, okay? The trick here is that you need to compare, okay? This is actually a weak acid, weak base case. So weak acid, what is the weak acid? You need to know that, okay, the weak base is ammonia, weak acid is HCl. Now, if you have like weak base, weak acid, again, you still follow the rule. Like if you have a salt that comes from an acid and base, the acidity is determined by the stronger side. And how do you determine whether ammonia is stronger or hydrogen cyanide is stronger? You need to compare the Ka and Kb. I think in the slide today, I think if I remember correctly, let me check my slide. Yes, yes. In the slide today, okay, if you pay attention to the slide today, page 67, okay, I think you can check yourself. The slide today, the midterm review slide, page 67, you know that, okay, if you have a weak acid, weak base situation, then you basically compare the strength of the acid and base. So you need to look up the Ka of HCN and Kb of the ammonia. So if you know that, okay, Ka is greater than Kb, that means acid is stronger than that is acidic. If Kb is greater than Ka, that means ammonia is stronger than that is basic. Okay, I don't remember the numbers here. I think ammonia is probably stronger, but I can't remember the numbers. If the Kb of ammonia is greater than Ka of hydrogen cyanide, then it will be basic. Okay, otherwise it will be acidic. You just need to compare the Ka and Kb to get the answer. Okay, will the value of Ka and Kb provided in the exam? Yes. For the exam, you should be able to finish the whole exam without bringing anything inside into the exam venue, although you are still allowed to do so, but all the necessary information accept the equation, but all the necessary numbers will be given to you. Okay, Ken, please turn to question 3 then. Okay, question 3. Okay, question 3, you assume that equal concentration of reactants and products are mixed, or predict whether the reactions would proceed to the right or to the left. So the general idea here is you need to look up the Ka values and Kb values. Okay, and if you check the Ka values, you are basically telling you that, okay, whether sulfuric acid is a stronger acid or ammonium ion is the stronger acid. For this case, it's quite obvious. Okay, for this case, you can see that, okay, sulfuric acid is clearly the stronger acid, and that's why the equilibrium will lie to the right. And the later one, you are basically comparing, okay, which side is stronger. If you have a stronger acid, you have a stronger base, then you are basically pushing always, like you are favoring the stronger side. Okay, so because the stronger side always want to dissociate. So if say this one you have a very strong acid, then you can check. Okay, then the strong acid side is going to dominate. So sulfuric acid is clearly stronger than ammonia, so sulfuric acid side is going to push to the other side. Okay, and the second one, 3B, is a similar idea. Ken, okay, also question 7, please. How do we know, there's another question, how do we know where if a molecule is basic or acidic? Basically, if you, how do I know if K is acidic? No, that is not, we will only talk about the acidity or basicity of a molecule of a salt or and not even an ion. Okay, when we talk about acidity, it must be related to a compound. We will not talk about whether an element is acidic or not, or basic. Or maybe you can DM like Ken, because I will talk on the screen. So if you want to have a direct message, maybe you can send to Ken so that he can answer that for you. Okay, on the screen, we will have question 7C. Okay, 7C. Okay, 7C. We are asking the pH of aqueous. Oh, I see. Okay. Okay, the pH of the following, sorry, I think I'm too close to the mic. Okay, so the pH of the aqueous solution of this thing at 25 degrees Celsius. You pay attention to the fact that, okay, this one is actually having an extremely small concentration. Okay, because this thing has a very small concentration, if you try to follow the rule, okay, negative log base 10 concentration of the acid, that will not work. Because if you take negative log base 10 of the concentration of the acid, you will get a number that is even greater than 7. Okay, you might get a number that is like 9 or 10, 9 point something. That does not make any sense because, well, this is nitric acid. Nitric acid should be acidic. So if that is dissolved in water, it should only give you a pH that is smaller than 7. If you find yourself, okay, dissolving an acid into water and get a pH greater than 7, that is clearly wrong. So the reason why is basically the proton concentration caused by the dissociation of this acid is even smaller than the effect of the water self-dissociation. And that's why in that case, the pH is dominated by the water self-dissociation, and that's why the pH is equal to 7 instead of like 9 point something. Okay, okay, so chapter 13. Yeah, I think we also have a chapter 13E. Did we finish the chapter 13, the question 13E of the current chapter? 13E. Oh, we have already finished that. Okay, then we move on to chapter 15, question 5. Okay, chapter 15, question 5. Okay, the Le Chatelier's principle. Okay, I see. So the idea here is like we have a salt, barium fluoride, barium fluoride. Barium fluoride, if I try to add different things, what will happen? Okay, the first one is hydrochloric acid. Hydrochloric acid, you need to pay attention to all the possible combinations. First, barium fluoride is what we want to study, so that is not important. But HCl, at least HCl is should dissolve in water because well, we know that HCl dissolve in water. So the other possible combination are barium chloride, which still dissolves in water because well, it is a chloride salt. Chloride salts, most of the chloride salts dissolve in water except for silver, mercury, and lead. But so the important part is the other side. So the important side is HF. Okay, if you have hydrogen fluoride, what happens? Hydrogen fluoride actually, because HF HF is a weak acid. So if you actually add proton to a solution of barium fluoride, basically the proton will take away some of the dissolved fluoride ions. Because some of the dissolved fluoride ions maybe it might be more convenient for us to write down BAF2. Okay, to BA. Yeah, I'm not going to draw it nicely, but yeah, you get the point. Okay, and 2F minus. Okay, so say if you have something like that, so if you try to add acid, basically you will interact with the fluorine or fluoride ions because like plus H plus, you will form HF. Okay, and HF is a weak acid. That means HF do not want to dissociate. So you are basically lowering the concentration of the fluoride ions, and that's why it will promote dissolution. Okay, so that is for A. B is common ion effect. You know that if I add fluoride, then I'm basically increasing fluoride concentration. I will push the dissolution to the left-hand side. So basically less solubility. Okay, lower solubility. Okay, third one is sodium nitrate. The idea is sodium fluoride, sodium do not interact with anything because sodium salts dissolve nicely in water. Nitrate salt dissolve nicely in water. So adding sodium and nitrate will not affect the solubility. Okay, because adding sodium will not shift the equilibrium, adding nitrate will not shift the equilibrium. Finally is the barium nitrate. Barium nitrate is another common ion effect. Just this time you are adding common ion of barium instead of fluoride. But that is also a common ion effect. If you try to introduce more common ions, you are going to push the equilibrium back to the left. Okay, you are pushing the equilibrium back to the left. So basically A is increased, B and D is decreased, C is unchanged. Okay, so that's basically everything. Okay, any more questions? Any more questions? Hopefully I'm not missing anything here. Okay, so if you do not have other questions, then we can end here. Let's wait for another 30 seconds to see if we have other questions. Okay, it seems that we do not have other questions. Okay, if we do not have other But do we need to do calculations for the previous questions of low concentration HNO3? No, you don't need to. As long as you recognize the fact that, okay, it only has a concentration of 10 to a power minus something greater than 7, okay? Because even water has 10 to a power minus 7. So if you have something 10 to a power minus 9, then you don't need to pay attention to that. Okay. Okay. If we do not have other questions, then we'll end the tutorial session here. Okay. Thank you very much. Thank you for coming, and thank you for staying with us for the whole semester. Thank you.